Hey everybody, I am going to go through the Waves exit ticket right now. There were 3 versions of these, one with a goose, one with a seagull, and one with a duck. The one I have right here is the goose. They all follow the main big concept. So if yours is a little different, pay attention to the big ideas to be able to apply this to problems with waves in the future. So, a student notices a goose floating on a lake that oscillates up and down 3 times during a 12-second interval as a periodic wave passes by. The student also notices that each crest of the waves is 1.5 meters apart. All right, what is the frequency of the goose's oscillations? Well, to be able to answer this, we have to know what frequency is. Frequency is how often the waves are happening per second. So how many full waves are we getting in a second? And we're told that we see this goose go up and down 3 times. And I could say 3, that means there's 3 waves in 12 seconds. That's the data that we have. If I simplify that, it turns into 1/4, and I'm left with a seconds on the bottom. And it turns out that's a hertz. 1/4 hertz, or if I wanted to do a decimal, 0.25 hertz, which means every second there's 0.25 complete waves. And that is the frequency of the goose's oscillation. The next question asks for the period of the goose's oscillations. In the same sense, we need to know what does period mean? It means the time for one full oscillation. And I can find it with the same data that I have in this problem. 12 seconds gives me 3 full waves. That turns into 4 seconds per wave, or a period of 4 seconds. That's what period means. It's the time for one full oscillation. And looking at the answers to 1 and 2 leads me to say, okay, these make sense because period is the inverse of frequency, and frequency is the inverse of period. Anytime you get an answer in physics, you want to ask yourself, okay, does that make sense? And yeah, 4 seconds for one full wave means you're only getting 1/4 of a wave every single second. That's how that works out. As far as the speed of the waves, well, I've got different ways to calculate the speed of a wave. I could use v equals f lambda, given in the equations up top. Or I could know that speed is a distance divided by a time, and the distance of one full wave is called the wavelength, and the time for one full wave is the period, capital T. In the problem, we're told that the crest of each wave is 1.5 meters apart. So if our goose is right here, goose 1.5 meters away is another crest. And that must be the wavelength. The distance from a crest to a trough is half of a wavelength. And the distance from crest to equilibrium is 1/4 of a wavelength. But in this case, the problem just gave us the full wavelength. It won't always do that, but it did here. So 1.5 meters multiplied by 0.25 hertz gives me a speed of 1.5 divided by 4 meters per second. And that can simplify. Let's see, 0.75 would be half of that, and half of that would be 0.375. I don't have a calculator, which is probably a bad choice. But that works out that is the speed of our wave. In the following scenarios, draw a wave pulse traveling towards the given wave that would exhibit the correct type of interference when the waves pass by each other. So, this problem asks for destructive interference. Draw a wave pulse traveling towards the given wave that would exhibit destructive interference with this wave pulse. Well, I would want to see something on the bottom. If this wave is acting in this string and pulling up, then I would need something to pull down to be able to cancel that wave. And a trough here will cancel out this crest. When these combine, the wave can't be in two places at once on the string, so the string can't be in two places at once, so they'll cancel each other out because they're on opposite sides. To exhibit constructive interference, let's put a wave on the same side, going towards this one. Those two, both on the upward side, will combine and become bigger. On the graph below, draw a transverse wave that fits the following criteria. Begins at a trough. So in a wave, the lowest points called the troughs, highest points called the crests, and this middle point, where if there was no wave, where would the wave actually be, are called equilibriums. Sorry, that might have been out of the picture. This crests troughs. All right, begins at a trough and has an amplitude of 1.5 meters. I can keep track of that right now and say, all right, 1.5 meters is right here, and that is going to be where my trough is. That is definitely a point on this wave. And anytime you're drawing a graph of something, whether it's a wave or a graph in math class or in econ, you want to think about key points that are there before you make the entire graph. The next thing I know is that I have to have a wavelength of 3 meters. So the next time I have a trough needs to be 3 meters away. That's a point on the graph. And then 3 meters after that is my next one, and 3 meters after that is my next one. All of those have to be troughs. And in between them have to be crests at 1.5 meters. And they're going to be up here at still 1.5 meters away from equilibrium, because my amplitude still has to be 1.5. And then I'll kind of bring these together. And there we go. That is 3 full oscillations with a wavelength of 3 meters and amplitude of 1.5 meters beginning at a trough. In math class, you would call this a negative cosine graph. So there we go. That is working through the exit ticket. There are blank copies of all the versions. Make sure you can go through them and you feel confident about all of your solutions. Thanks for watching.